This lesson is on section 4.1, polynomial functions and modeling with polynomials. First of all, a polynomial has this general form, and if this looks confusing, we will discuss what it is down here. The a sub n is just a coefficient, and so the a sub n, the a sub n minus 1, a sub n minus 2 are just representing the numbers that would be in front of those x's, like the 5, 3, and the 7/2, and the 9 down here. Then x's are two powers, and we generally put them in a form where the highest power starts on the left and you work your way down until the last number is a plain number without an x. So this n minus 1, n minus 2 here represent things like 4, 3, 2 when you are writing out a polynomial. We need to know what these things are called sometimes. The numbers, and I'm going to come down here, are called coefficients. And so the first one with that highest power of x when you have it lined up is called the leading coefficient. And the whole piece, the whole first piece, is called the leading term. Each piece is a term. So this 5x to the fourth is our first term, or our leading term. Negative 3x cubed is another term. 7/2 x squared is another term. 9x is another term. Negative 1 is another term. And these could, the amount varies depending on the powers and what you have. But you need to especially know the leading coefficient and the leading term. Okay, here I've listed some polynomials and some things that are not polynomials. If you'll notice, all of our polynomials have x's as bases, and the powers are numbers that are positive integers. This f of x equals negative 3 is also considered a polynomial because it could be x to the 0 here. The non-polynomials, we have things like absolute value, square root, fractional exponents, which would mean that it was also a root, or fractions in general. So these are not polynomials, these are. Things you need to know about polynomials is that they are all continuous. All these polynomials are continuous, and we're going to be talking about the shapes of the graphs in this section. The domain of all polynomials is negative infinity to positive infinity, or all real numbers. So if you're asked about the domain and it's a polynomial, it's always going to be the same answer. So those two things are important to keep in mind. Now, there's some basic shapes that you should know, and y equals x is one of those. If I had an x and y axis here, y equals x is your linear function, and it's a perfect line with a slope of 1 going through 0, 0. Just your perfect diagonal, but that's your basic linear shape. Y equals x squared, we should be familiar with, is our parabola, and that is your basic quadratic shape. And then I'll come over here to these higher powers, which you may or may not know. X cubed graph is something like this, and that is considered cubic. And x to the fourth graph, it's really similar to a polynomial, to a quadratic, except it's a little flatter sort of at the bottom, and this has a name, it's a quartic. Like quarter, but quartic. And the thing about these shapes over here is the changes that can be made by adding, x's and numbers onto them. That's when you get the little hills and valleys in there. The quartic can sometimes look like almost a W. A cubic can do a mountain and a valley. Negatives can flip them and they turn different way, or flip down. So changes can be made, but you should know the basic idea of the shape before those changes are made. So kind of building off that, even degree. means that the highest power of that polynomial is an even number, just like 2 and 4, the quadratic and the quartic from above. Things that have an even degree will have some sort of U shape or W shape, and they'll either face up or face down. Okay, but they'll have that same general shape. They'll start and end pointing in the same direction. Odd graphs are things that are odd degree, are things that have something like 3, 5, 7, 9 as the highest power of x. All of those will kind of follow that cubic. They will either do some sort of shape where they start low and end high, or if there's a negative involved, they will start high and end low. Now, what happens in the middle, like in this section or in this section of the graph, can change. There can be hills and valleys and different things going on in there. But the ends will still work the same way. They'll start low and end high, or start high and end low. Same thing over here. If they started going up, they end going up. Different things can happen to these middle sections of the graph. And so we're not going to stress about those right now. We're going to be talking about the ends. Okay, and what we're going to use to do that is called the leading term test. And the leading term, obviously that first term that we mentioned, we look at the number in front, the leading coefficient, which in this case we're calling A. And if our function is even, so U-shaped graph, and A is positive, then it's going to face up. And if A is negative, it's going to face down because it will have had a vertical flip, as we've studied before. Now, the way that we use the leading term test is to talk about what happens on the ends. And the way it's worded here, let's take the positive A, say that we're face up. We will talk about the end saying as x goes to infinity, that would be this right end, because x would go to infinity to the right. What is happening? Well, this graph will be going up. So as x goes to infinity, y goes to infinity. On the other side, this arrow here, that's where we're going to the left. So x's are going to negative infinity. What's happening to the y values? They're also going up. So the y's are going to infinity. So as we go to the right, the y's go up. As we go to the left, the y's go down. Okay, we're just writing that mathematically. If we have an even function that's face down, like this one here, let's talk about those two situations, as x goes to infinity and as x goes to negative infinity. So as x goes to the infinity, I'm looking at this right side. What's happening to the y values? They're going down, so y will be going to negative infinity. As we look at the left side, x is going to negative infinity, then the y values are also going down, so y is going to negative infinity. So it's just talking about the very ends of the graph in these mathematical statements. Okay, odd functions. If we think about an odd function with the leading coefficient being positive, then that's one that would start low and end high. And so again, we want to address what happens as x goes to infinity and what happens as x goes to negative infinity. So positive infinity is to the right. So I'll look at the right end, what's happening? The y's are going up. So y goes to infinity. The left side, as x goes to negative infinity, will be over here. What's happening? The y's are going down. So y will be going to negative infinity. Okay, if that leading coefficient is less than 0, so it's negative, it will have had a vertical flip, and it will be doing the opposite. So again, x goes to infinity and negative infinity. What's happening to our y's? So as we go to positive infinity, that's the right side of the graph, the y's are going down, so y goes to negative infinity. As we look at the left side of the graph, x going to negative infinity, the y's are going up, so y goes to infinity. Alright, so examples of how they're going to ask you to use this. They want you to use the leading term test to describe the end behavior of each. In other words, we're not going to plug this in our calculator to see what the graph looks like. We should know what the graph looks like based on the power and the coefficient. So based on the fact that a has a power of 4, it's even, and the 3 is positive, it is some sort of face-up u. So my answer would be what I answered for the face-up u, as x goes to infinity, y goes to infinity, and as x goes to negative infinity, y goes to infinity, because they're both going up. Part B, it's an x cubed graph, but the leading coefficient is negative, so it has a vertical flip. So it's going to be sort of like this. Again, I want to address what happens as x goes to infinity and what happens as x goes to negative infinity. So as x goes to infinity, the right side, y is going down, so negative infinity. As x goes to negative infinity, which is the left side, y is going up, which is positive infinity. There's 2 more examples here. It would be a good time to pause and see if you can do those on your own. Okay, for C, because it's an x to the 5th, that's an odd power, and the leading coefficient is a 1, understood. We know that it's going to be the regular cubic look, or odd look, I should say. So as x goes to infinity, y is going to infinity. And as x goes to negative infinity, y is going to negative infinity. For D, it's an even power, so it's a U shape, but the coefficient is negative, so it's going to be face down. So as x goes to infinity, y is going to negative infinity, and as x goes to negative infinity, y is also going to negative infinity. Okay, example 2. We have a polynomial given to us, and they just want us to determine whether the numbers 2 and 5 are zeros of that polynomial. The easiest thing to do is just plug those in and see if you get 0 out. If they are a 0, you should be able to plug them in and get an answer of 0. So I'm going to see what p of 2 is. So I'm going to plug that in, get 2 cubed plus 2 squared minus 17 times 2 plus 15. And if I calculate that, I'm going to get a negative 7. So 2 is not a 0. Now I'm going to plug in the negative 5 and check it. So I'm going to say negative 5 cubed plus negative 5 squared minus 17 times negative 5 plus 15. And when I plug that one in, I do get a 0. Now, if you're typing this in your calculator and you're not getting 0, you're probably not putting your parentheses around the negative 5. Your calculator needs that negative with the 5 before you cube it, so it needs to be in parentheses. So my answer to this would be that negative 5 is a 0, 2 is not a 0. Now, before we move on, I have a statement here that's important that most of you know anyway, but the number of zeros that you get, or answers that you get, this is real and imaginary both, should match the power of the leading term. So, in other words, if it's an x to the 4th, then you should get 4 zeros. If it's an x cubed, you should get 3 zeros. Now, they're not all real numbers. Sometimes you get i's as answers, but you should get a total of however many that the power is showing. Okay, so to find the zeros of this, we're going to do this algebraically, and this one is very nicely already factored for us. You basically set each piece equal to 0. So I have 5x equal to 0. X minus 2 is cubed, so technically there would be 3 of these if I wrote them out, but they're all going to solve the same way. I'll talk about that in a minute. And then x plus 1 equals 0. So if I divide by 5, I get x equals 0. If I add 2, x equals 2. And if I subtract 1, x is negative 1. So these are 3 places where our graph is crossing or touching the x-axis, and they are considered our zeros. Now, this middle one is going to count 3 times because this was to a power of 3. So I do technically have the 5 answers that I need. I have 1 here, and 3 here, which adds up to 5. And again, I'll go into a little more detail in just a moment. Okay, so we now have another example, number 4. I'm doing the same thing. So to find my zeros, I'm going to set this x minus 1 equal to 0 and this x plus 2 equal to 0. I do have this negative out front, and like in the last problem I had the 5x and I set it equal to 0, but if you take that negative understood, negative 1 equals 0 doesn't make sense, and so you're throwing that away anyway. You really don't have to worry about it unless it has an x with it, and if it has an x with it, whatever that leading part is, then that does need to be equal to 0, just like we did in number 3. When I solve these, I get x equals 1 and x equals negative 2. But again, because of these squares up here, this one technically counts twice and this one counts twice. So I'm getting the 4 answers that I need. And that is actually called multiplicity, which is our next little thing. Multiplicity is how many times you get a particular zero for a function. So in example 3, let's say 3, if you scroll back up and look, we got x equals 2 as one of our answers. We would say that was x equals 2 with a multiplicity of 3 because it counted 3 times. In example 4, we had x equals 1 with a multiplicity, and I'm just going to abbreviate, of 2 because it counted twice. And x equals negative 2 was our other answer, and it also had a multiplicity too. We don't typically write answers that have multiplicity of 1, that's why I didn't write everything from in number 3. I mean, we just list those, but we don't say multiplicity 1. So you can just list those if you're asking, or you're answering a question and you just have the answer counting once. Okay, to understand what that does to a graph, if the multiplicity is even, so like these up here that were multiplicity 2, the graph is going to bounce off the x-axis. And so it's tangent to the x-axis. So the graph is going to do this at that point. So for our example 4, it was bouncing off at, let's say, negative 2. Now, I don't know, I haven't graphed this to see which way it bounced. It could have looked like this, or it could have bounced off from underneath. The point is, if this number here is even, multiplicity 2, multiplicity 4, multiplicity 6, the graph will bounce off of the axis. That's the shape that it's going to be given. If the multiplicity is odd, so the 1 that we don't write, the 3, if it counts 3 times, like in example 3, those kind of graphs go through the x-axis. They cross through the x-axis. Usually if something is multiplicity 1, it's a really clear, going right through it, obvious thing. If it's a multiplicity of 3, or 5 or 7, it tends to maybe flatten out a little bit sometimes as it goes through the axis, but it still crosses from the negatives to the positives or the positives to the negatives. But that's the main thing, is to know what happens. If it's even, it's going to bounce. If it's odd, it will go through the x-axis. I do have another statement here that you need to remember, and that's that the higher the multiplicity is, the flatter the graph is going to get at that point. So on this odd one here, I said, if it was a multiplicity of 5 or something like that, it would get really flat right there. It also happens in the evens. So if you have multiplicity 4, multiplicity 6, multiplicity 8, you'll have the graph going, bouncing off, but getting really like almost flat at the bottom there. That's how the graph shows that it's counting more than once. Okay, example 5, we're going to be finding the zeros of this, and we have to do a little more work. It's not factored for us. This one, because it has 4 pieces, it actually is factored by grouping, which you may not have done in a while, but you group the first 2 together, group the second 2 together, and then you take out a GCF. So in the first section, x cubed and negative 2x squared have x squared in common. That leaves you with x minus 2. In the second grouping, you have a 9 in common, but I'm going to take out a negative so that what is left matches what I have over here. So if I take a negative 9 out, that's going to leave me with x. It's going to change the sign because I'm taking out a negative here. So x minus 2. And then by factor by grouping, I look at this line and I see that I have a GCF again, which is x minus 2. And if I take it out, that leaves me with x squared minus 9. Now we know that that's going to factor again. So x squared minus 9 will be x minus 3 and x plus 3. And now I can set all of those equal to 0 and solve them. So I have x equals 2, x equals 3, and x equals negative 3. I have 3 zeros. The highest power of my problem was 3, and so I have found all the answers. They happen to be all real answers, and they're only counting once. So this graph should cross through the axis at each of these places. Example 6, again we're finding zeros, and this one's not factored for us. You'll notice that this goes from 4 to 2 in the powers, so this is a u factoring situation, and I'm going to let my u be x squared. That'll make this u squared plus 4u minus 45. And then I'm going to factor into 2 parentheses, and I'm going to come over here and do my x factor. 1 times negative 45 is negative 45, and then I have the 4 from here that goes down here, and I'm asking myself what's going to multiply to give me 45 and combine to give me 4? 9 and 5, definitely, but I need to multiply to get a negative. So one of these has to be negative, and I need the 4 to end up being positive. So that has to be the 5 that's negative. So I'm going to have u plus 9 and u minus 5. And if I set those equal to 0, and solve, I get u equals negative 9 and u equals 5. And then I'm going to substitute back in. X squared equals negative 9 and x squared equals 5. Here, if I take the square root, I get 3i and negative 3i. Here, if I take the square root, I have to look at that as the positive and negative. So I have the positive square root of 5 and the negative square root of 5. So I have 4 answers. 2 of them are real, 2 of them are imaginary, but I do have 4 answers, and that matches the power of the polynomial. Example 7 is just thrown in here to make sure you know how to find the zeros on your calculator, and we have done that before with our quadratics. So if you will type that in your y1 and graph it, and I'm just going to sketch it right here. You want to be able to see where it crosses the x-axis, and that's nice. I can see that it crosses 3 times, and I should because I have 3 solutions here. And then you use your calculator by doing second calculate the zeros. And you have to do the left bound and right bound, so you have to be on the left side of the point and the right side of the point. And then you can hit enter. And this first one ends up to be negative 1.68. Then you have to do second calculate zeros again, and the left side and the right side happen to be above and below this time, the opposite of what you had before. But you hit enter on each of those, and you should get this one to be 2.154. And then you have to do it a third time. So second calculate zeros, left bound enter, right bound enter, and you get 5.526. So we have 3 zeros here. They're all real numbers. They're just ugly. And that matches our power, so we're good. And we move on to our applications, our word problems. Our first one, we are given a polynomial function that can be used to estimate the number of milligrams of the pain relief medicine ibuprofen in the bloodstream T hours after 400 milligrams of the medication has been given. Find the number of milligrams in the bloodstream at time 0, time 0.5, time 1, time 1.5, and so on up to 6 hours. Round the function values to the nearest tenth. Now this is asking you to do a lot of plugging in. They're wanting you to plug in 0, 0.5, 1, 1.5, and everything up to 6 hours. Okay, that's a lot of information. So I'm going to teach you how to use your calculator and help yourself plug in faster. So what you want to do is go to y equals on your calculator, and if anything is in your y equals, clear it out and type in this polynomial into your y1. Once you have it typed in, hit second quit. Then you'll be on a main screen, and you will go hit the VARS button, which is right beside of the clear button, VARS, and a menu pops up. At the very top, you want to arrow over to YVARS, and it should be on number 1 function. Hit enter, and then it comes up and it's on Y1, so hit enter. And then open up a set of parentheses, type in 0, and close your parentheses. That will do the math of plugging that 0 in. And obviously if we plug in 0, we should get out 0 here in this case. To go to the next one, you don't have to redo everything. It's already in Y1. So hit second, enter, and it comes up with what you typed in. Arrow back over the 0 and put in 0.5. And then hit enter. And that gives you 150.2. Now, you can just hit second enter again, and it's going to pull up that Y1 again, type over it, put in 1. If you are needing help with this, it's going to make this problem go a lot faster. If you need help with this, raise your hand, and I will come and help you and show you where I'm talking about things on your calculator. I'm going to go ahead and list out everything that you should be getting here, but you need to make sure you know how to do this. Okay, so if you've plugged in correctly, these are the answers that you should get, and it would have taken a lot longer to do it individually by hand, plugging in every time, and with a lot more chance of error. So again, if you did not understand what I was saying on the calculator, please call me over and I will help you, because it's going to make life a lot easier in this type of situation. Okay, part B is asking us to find the domain, the relative maximum, where it occurs, and the range. So the domain, if we look at these input values, we can tell we started off with 0 and obviously initially took that and it started to work in the system. It went up into the system and then it started working its way out, and by hour 6 we were back to 0. Our domain is those times, and so the domain is 0 to 6. So it was in our body from 0 hours to 6 hours, and then that was the end of it. Now, the relative maximum, you can kind of guess where it is, because if you look as it was, building up and getting into your bloodstream, it happened somewhere right in here because we hit the highest numbers here, but we have to use the graph to actually figure that out. And then the range will be specific when we look at the graph. So since you already have it in Y1, just graph it and find a decent window. You may want to make your x's go from 0 to 6 and your y's go from 0 to 500. That's what the book suggests. If you do that, the graph will look something like this. And that highest point you can calculate doing second, calculate the maximum, and we get that occurring at 2.148 and 345.76, basically 2. And so we can answer the questions now. Here's our relative maximum. The amount is the 345.76. That would be what we would answer this question with. The where it occurs is this time of 2 hours, 2.148 hours. And then our range, obviously the lowest it goes is 0, the highest it goes is the y value we reach here. And so our range is from 0 to 345.762. So that's how we use that graph to answer those. Okay, here's example 9. It has U.S. Army personnel on active duty making up approximately 37% of the total number of the U.S. military. Mid-year numbers in thousands of Army personnel for selected years are listed in the following table. So we have this table, and obviously they're counting year 2005 as 0, so you have to be careful with that. And they say look at the table, and it could be modeled with a quartic, a quadratic, a cubic. It could be modeled with some polynomial. Your calculator has the ability to calculate equations in quadratics, cubics, or quartics. So part A, what they want you to do is model the data with a quadratic function, a cubic function, and a quartic function. And use not the year, but the 0, 1, 2, 3, 4 type thing. And then look at the r squared value and decide which one is the best fit. We're going to look for the r squared value that's closest to 1 or -1, probably 1 in this case. But what I want you to do, because this takes a little bit of time, and I think you've done regressions before, is turn to page 229 so that you can see the outcome that you would get. If you need help with how to do a regression, you plug them in under your Stat button on your calculator, Stat Edit. You want to type your x values in list 1 and your y values in list 2, and then you want to do second quit, and then hit Stat again. And under the Calc menu, not the Edit menu, the Calc menu, number 5 is a quadratic, number 6 is a cubic, and number 7 is a quartic. They're using those regressions, and that's how they're coming up. They have screenshots on that page 229 of what you get with the quadratic, the cubic, the quartic. And if you look at the r squared values for each, on the quadratic you have a 0.928, on the cubic you have a 0.981, and on the quartic you have a 0.9979. So the one that is closest to a positive 1 is the quartic. That means the quartic is the best fit. And so in part B, when they ask us to graph the function with the scatter plot of the data, you will have to turn your scatter plot on to see it, and you will have to put your quartic function in y1. If this is something that you need help with, please call me over, because I know that this is getting long and I want you to be able to do it, but I want you to be able to focus on it. So this is definitely calculator work, and call me over to help explain how to do those regressions. And I'm going to stop here and let you, look at that page 229, ask questions if you need to, and then end this lesson. Thank you.